Really, a great pleasure to have Lance Dixon here. So a little, maybe it's not a little known fact, but we've written almost 100 papers together. Not quite.
That counts conference proceedings too, doesn't it?
It could, yeah. But we're pretty close to 100, so we should work on that.
Okay.
In the meantime, Lance is going to give us a talk on antipodal self-duality and planar n equals 4 super Yang mills and Fishnets. Please go ahead.
Thanks, V. It's a great pleasure to speak here. I was a frequent visitor here in the 90s and 2000s and maybe early 2010s. And so it's great to be back here. I think this is the first time I've spoken in the Schwinger Lounge, though, maybe. But anyway.
I think you spoke here.
What?
I thought you gave a journal club. Okay.
I don't know. Maybe I did. Yeah. Okay. I remember speaking over in that room quite a bit. But anyway, so yeah, back in the day, we were working together on QCD calculations for the LHC. But we kind of built some of the tools for doing it by studying what happens in a simpler theory, which is QCD's maximally supersymmetric cousin, planar n equals 4. And then I got interested in amplitudes in this theory, and I've been looking at them for a while, and we've been able to compute them to pretty high orders and examine certain patterns that appear in them. And we found something that kind of knocked my socks off. It's still a little bit obscure, so but it's a very weird symmetry where you take maybe two different processes and you take the result for one of them, and in a certain sense to be defined later, you write it backwards. And then it becomes the answer for the other process. So that was pretty bizarre. And then we found another process that you transform it into the same process for different kinematics. After writing it backwards, it becomes the same. So that one we call antipodal self-duality because it involves the same process, whereas the original one was antipodal duality. Now the problem is we've been looking for more examples of this and we haven't found that many of them. So we're a little stuck, but then we decided to look in another theory. So planar n equals 4 super Yang mills is a kind of toy model for QCD, but there's another theory, Fishnet theory, which is a toy model for planar n equals 4. So or rather it's a strong deformation of planar n equals 4. And it's so strongly deformed that there are no more gluons left in the theory. And in fact, in one case, there's no fermions either. There are just two types of scalars that interact with each other through a non-Hermitian phi to the 4th. That's these black solid lines and dashed lines. And so every kind of observable turns out to be a single Feynman integral. So now we can find examples of this, this kind of symmetry happening in that theory. So that's the more recent stuff from the last year or so. So that's sort of one version of the outline. And here's another version in words, but I can go through this briefly because I more or less just said it. We have this very strange symmetry. Now, in order to explain the symmetry, it operates on the functions, and you have to know a little bit about what the functions are like. So I'll describe to you what the functions that are involved are like. They're all multiple polylogarithms, which are certain classes of iterated integrals. And these functions have a mathematical property called a Hopf algebra. So they can be decomposed into simpler pieces by something called a coaction, which splits one function into two. And the maximal iteration of that to break things up into sort of the simplest pieces gives you something called the symbol. And this antipodal self-duality, it doesn't take a function into the same function, but with different field variables, it really changes the function because it involves writing this symbol backwards. And there also has to be some kind of kinematic map, or how you decide where you are in one process and where you are in the other process. But this business of writing the symbol backwards, that's called the antipode of the Hopf algebra. And it does weird things to the function. So branch cuts or the discontinuities when you move in certain directions, those get exchanged for derivatives or small changes in the argument. So it's a pretty weird operation. So as I was saying, the new thing is we can see how these transformations can be implemented and invariants can be established for certain individual types of integrals, some cases which are also amplitudes, and those will be the fishnet integrals. So the hope is that we might be able to understand through some of these even simpler examples what is the physics or mathematics underlying this kind of symmetry, but we don't yet have a good interpretation. So reversing words. There's a notion of palindromes, which is where you write the same word backwards and forwards and you get the same answer. In fact, the logo for this band recognized that it was the same written forward as backwards. But we're talking about things where you write something backwards and you also combine it with a transformation on letters. So like maybe you have a word that's the same when you write it backwards, but you first have to do some kind of substitution rule on the letters. For example, you might have to exchange B and R and C and D at the same time you reverse the letters. So that's what happens with abracadabra. If you reverse it and you also transform the letters by swapping B and R and C and D, it comes back into itself. So that's kind of an example of the kinds of things we have at the level of letters of the symbol. Still have to tell you what the symbol is though. So the theory we're going to look at, as I mentioned, it's kind of a toy model for QCD, and it's a case where we can compute very analogous processes to things you would do in QCD for the LHC, but we can go much further in the loop expansion. So we can collect a lot more theoretical data. So the theory, we add n equals 4 superpartners of gluons, so 4 gluinos and 6 scalars, and we take the gauge group to be not SU3, but SUNC, where NC goes to infinity, and that corresponds to planar diagrams. And it's known, or at least heavily suspected, that in this limit, the theory is integrable, and there are many symmetries you can find. Also, the amplitudes have a much more constrained kinematic structure. These rational prefactors, well, any function that involves transcendental functions might also have simpler prefactors called rational prefactors with rational dependence on the kinematic variables, whereas polylogarithms are transcendental functions. In the case of n equals 4 super Yang-Mills, this rational structure is much better understood than in QCD. And it's essentially given by looking at the tree amplitudes, maybe in the BCFW framework, typically gives you this rational structure. And in our case, the rational thing will just be a single tree, a single rational prefactor, which is also the tree amplitude, and then a single transcendental function multiplying it, which we want to compute at each loop order. So we're going to be able to focus heavily on just the transcendental functions. In fact, I won't even mention what the rational functions are. Also, all of these amplitudes are amplitudes for specific particles at a specific order in perturbation theory, and they're all infrared divergent. But I'm going to assume we've divided out by the known form of the infrared divergences. So there's a function called the BDS or BDS-like ansatz that takes care of that. So we basically will have a sequence of transcendental functions, and there's going to be some mysterious relations between them that we're going to try to see if we can understand. So back in 2021, we just discovered empirically that when you take this particular process and apply this antipodal transformation of writing the symbol backwards, it maps into this particular process. So this process has a single operator, which is a very simple BPS operator, sometimes called the trace of phi squared, or the chiral part of the stress energy tensor in this theory. So you take the matrix element of this operator with three plane wave states. Well, it also has a representative which spits out two gluons, the trace of F nu, F nu. And then you take the three gluon matrix element of that operator. And then on the other side of this duality is the 6-point maximally helicity violating 6 gluon amplitude. So you look at the relevant transcendental functions here, and you construct something called the symbol, which has a sequences of letters, and you write the letters backwards and keep the coefficients the same, and you find that they just map right into each other. And we had data up to 7 loops, 8 loops on this side and 7 loops on this side, and everything matched perfectly. And then we got 8 loop data here using this symmetry. So then about a year later, we realized that we could kind of understand this symmetry if there was another symmetry. And that symmetry involves a form factor, very much like this one, but with one more gluon in it. So this is a more complicated object. This one depends really on 2 variables. This one depends on 4 variables. But if you go into a particular limit, it goes smoothly into this one. And that's the limit where 2 of the gluons are parallel. But you can take another limit where 3 of the gluons are parallel, and then it turns out that it goes into this object. So if we could find, and we could find, a self-duality that maps this guy into the same process, although at a different kinematic point, we could potentially explain this symmetry. And it actually works in the sense that this kinematic map that we found, when we go into this limit, the point of phase space that you're in maps over to this point. And in both cases, the symbol reverses at the same time. So now we have a structure up here that explains this property, but we still don't understand this one. Any questions so far?
So the one that goes from the F4 to the A6, that looks pretty unobvious.
It's very unobvious, but fortunately, you and I wrote a paper together in 2008, which pointed this fact out.
I can go read that paper.
Yeah, it was a good paper. I had to remember it too, because I first kind of understood this in a more recent way, and then I realized we'd seen this before. So the way it works is that the 6 gluon amplitude has a triple collinear limit. Okay, so in that limit, it's the 4-point amplitude, which we know is kind of trivial, right? It's just given by the BDS ansatz. So we're going to like divide out all the infrared divergences, and then that 4-point thing is like 1. It's like there's no kinematic dependence in there. So in this triple collinear limit here, this becomes a triple collinear splitting function. And we also pointed out in that paper that the essential dual conformal invariant piece of this answer, the remainder function, it actually doesn't move in the triple collinear limit. So it's actually the same as in the bulk kinematics. And the point is that this thing does move in the triple collinear limit, but it moves to become equal to what this thing is.
I better go read that.
Yeah, you should go read that paper.
It's like really interesting paper.
Any other questions? But I totally agree. This is non-obvious and doesn't happen in a generic theory, whereas this is pretty standard when you take 2 guy's collinear, there's can be a splitting function, but it's kind of removed by dividing out the infrared divergences. And so that part's more obvious. So this other theory we want to talk about is strongly deformed planar n equals 4. And this one was invented much more recently than the by Omer Vertigan and Volodya Kazakov, also with Caetano. You take the Lagrangian for n equals 4 super Yang-Mills, and you suspect it has integrability. So you want to, there's a particular way to deform the theory by boosting the superpotential in a particular way. And the superpotential dictates the matter interactions. And there's also a coupling in front of it, gauge coupling, and you reduce that at the same time you increase the superpotential so that the matter interactions survive, these pieces of them, but the gauge interactions go away. So you don't need any gluons anymore. And there are a couple of different limits, and some of them include fermions, but by far the simplest limit is one in which all the fermions go away as well. And the only surviving interactions are some interactions between two complex scalars that look like 5 to the 4th interactions. Except they're non-Hermitian because there's a kind of definite ordering from the planar limit around the loop, and the z's and z daggers don't kind of respect are different when you flip the diagram over. So if you look at just having this vertex and you consider something that's a 4-point correlation function with a single trace around the whole thing of products of these x fields and these z fields, you find you can only write down one diagram. So if you have like m lines this way and n lines this way, you get a thing we call a rectangular fishnet. And this is a function of two variables. There are two conformal cross ratios, often called u and v, that are the conformally invariant quantities made out of these 4 points. But it's traditional to rewrite them in terms of complex variable z, and this is one way of doing it, writing them in terms of z and z bar. So all of the amplitudes in planar n equals 4 are shown here to every loop they've been computed, and all of these fishnet integrals can be described by a class of functions called multiple polylogs. And at L loops, all of those functions, there's a grading on the functions of the multiple polylogs, which means there's an integer you can associate with each one, which is just the number of iterated integrations. And furthermore, in this n equals 4 super Yang-Mills theory, the answers always turn out to have a weight, which is twice the loop order. So we have a specific place we want to be in this grading. And then these functions are iterated integrals, which are iterated d logs. So this is the differential of the log of t minus a1, where a1 is some external parameter. And it is an integration of something which also was an integration of. And so when you undo this recursive formula, you find that this guy has n integrations, or weight n. And so that's what's set equal to 2L. And then there's some special cases when the a's are 0 that you have to define as logarithms. So, yeah.
Why is there a factor of 2 between n and l?
Sorry. Well, the heuristic way of thinking about it is in 4 dimensions, we have to do 4 integrals over the 4 components of the loop momenta. But 2 of them kind of give us just I pi's. So we have 2 trivial integrals per loop and 2 non-trivial integrals per loop. So in 1 loop answers, you often get dilogarithms or log squared. That's the worst you've ever seen in a 1 loop integral. And each successive loop gives you two more of these. Now, in non-supersymmetric theories, we often have lower weight answers. For example, the beta function in QCD. That's a 1/epsilon pole, and it's not a lot. Normally, you would say one loop would be weight 2 or log squared for a finite part. But also a 1/epsilon kind of counts as a logarithm, typically. And it definitely does in the n=4 world. So you would expect that a 1/epsilon should have a logarithm in it, but the beta function is a rational number, 11/3 Ca minus 2/3 Cf. So that's an example of something which has a lower than maximal transcendental weight, but it's also 0 in n=4. And so n=4, you get this very uniform weight. In a generic gauge theory, you get objects of lower weight than the maximum. So this is always the maximum, and it's always saturated in the n=4 world. Why? It's not completely clear, but you just end up getting those types of integrals. Any other questions? So I gave you an integral definition of these multiple polylogs, but it's somewhat easier to think it maybe in terms of a differential definition, and you can show that they're equivalent. And in the differential definition, you think about a whole space of functions. You have a function that you might be interested in of weight n, and then you take its total differential. So you study how it varies in all directions in the phase space. And if it's a multiple polylog, it will have the form of a discrete number of terms where the only sort of rational stuff is a differential in the logarithm of some variables, sk, and they're called the symbol letters, and they belong to L, the symbol alphabet. And then these FSKs, they are transcendental functions too, but you've removed one of the integrations, so they have one lower weight, weight n-1, if this had weight n. Now there's a more general Hopf algebra, which splits these functions into bigger pieces, but the derivative is one piece of this Hopf algebra, and we call it delta n-1, 1, because it's the part where you split it into weight n-1 and then weight 1. But you can split it into any two integers less than n if you want to. So we call this action. This is called the coproduct or the coaction, depending on how technical you want to be. So we call this the n-1, 1 coproduct of the function. And you can iterate this. So you can take the differential of one of these coproducts, which is labeled by an index which says which letter you have. And then you get the same formula, but now you just keep the SJ in the back to remember which one you started with. But otherwise, it's the same as the previous formula. You have a sum over these symbol letters SK. And that would define a double coproduct, or which has sometimes called n-2, 1, 1, and has weight n-2. And then you just keep going. And at the end of the day, you have peeled off all of these logarithms. I should have said before, when you do this the first time, you have a differential structure, but then you promote it to a tensor product, and you sum over tensor products. And each time you do this, you get a new tensor product appearing. And at the end of the day, for weight n, you have n tensors, which should really be logarithms written here, but we just omit the logarithm as implicit. So it's a big tensor in the symbol letters, and then the tensor coefficients are written here, and these are always rational numbers. And in our examples, they always end up being integers. So a simple example where you can apply this technology are the classical polylogs. So the Li1 is defined to be the minus the log of 1 minus x. or the sum over k of x to the k divided by k is its series expansion. And then if you write x to the k over k to the n for n greater than 1, it's easy to see by integrating term by term that there's a recursive generation of this polylog of weight n by integrating dt over t. So if you rewrite this by differentiating it, you see that the derivative of this is ln minus 1 of x divided by x, or that the differential is ln minus 1 of x times d log of x. So that d log of x tells you that the symbol of lin is the same as the symbol of lin minus 1, but you get a tensor x because you found a d log of x on the back. And then you iterate this relation. So you peel off n minus 1 tensor x's at the back, and then you write the symbol of log of 1 minus x, which is just 1 minus x. So this is an example of the symbol of a simple function. And it illustrates something, which is that the branch cut discontinuities are described or characterized by the first entries. Where does this logarithm have a branch cut? It's where x is equal to 1, which is also where this radius of convergence of this series is at 1. So branch cut opens up at x equals 1, and that's where the leading letter or only letter goes to 0. But these are given by integrals of that same function with the branch cut. They all iterate off of that, and that branch cut stays there. And it's illustrated by the fact that these symbols all have that 1 minus x in the front. Whereas the last letter, x, that was the clue that the derivative was d log of x. So the last entries tell you about the derivatives, and the first entries tell you about the branch cuts. So if we have a symmetry that reverses the letters, it's going to mix up the role of branch cuts and derivatives in some weird way, among other things. Okay, here's another example of the symbol. First, this product of, when you have a product of two logarithms, of any two functions, the symbol, because of the Leibniz rule for derivatives, you do things in both orders. So you get a d log y term that gives you this contribution, and a d log x term gives you this one. So you get this sum of products. And also, the logarithm of xy is the log of x plus the log of y. We just leave the logs out by convention. So you can have these two identities. And then we go look at an integral that was computed back in the 70s by Hodges and Bloch and Wigner, and studied many times since then. And it's called the one loop box integral with massless internal lines and arbitrary external masses. And up to some rational prefactor we're not going to worry about. It's a dilogarithm and logarithms, but it has a special property that it's actually a single value. So in the z-plane, complex plane, when you take z around the origin, well, you can see these guys are regular near the origin, and this combination is regular too as you go around the origin, because the phase doesn't change. And this thing is also single valued at z equals 1, which is a little harder to see in this representation. Anyway, as we learned earlier, the symbol of this guy is 1 minus z tensor z, and then the complex conjugate part. And then by using this formula and this formula, you can work out the contributions to the symbol from these logs. And after some work, you'll find out that it has this form. The fact that the ZZ bar appears in the front, that is related to this single valuedness. And similarly, the fact that 1 minus Z comes with 1 minus Z bar. And the things sitting behind these two first entries are these two last entries, which are ratios of Z and Z bar. And the symbol alphabet, or the total number of different objects that appear here, is 4. So Z and 1 minus Z, and Z bar, 1 minus Z bar. And we'll see that this guy actually has an antipodal self-duality. How does that work? So we want to look for a symmetry where we reverse front and back, and we also can do some manipulation on the letter map or some kind of transformation. And a thing that works is to just do complex conjugation, but with a slight twist, where the barred guys get inverted, or at the level of logarithms, you put in an extra minus sign for every weight associated with the anti-holomorphic guys. So you see this 1 minus Z bar, we're going to move it to the back, but we're also going to flip over the conjugate one, so it looks like this. And then the Z over Z bar, we're going to move it to the front, and then we're going to flip over the back one. And we end up getting an invariance of this symbol under this operation. So this will also be the operation that will leave invariant all square fishnets, it turns out. And 1, 1 is the first example of a square fishnet. Any questions? So the guys we were talking about before in the undeformed planar n equals 4 were this chiral stress tensor BPS operator with these 3 particles which carry massless momenta. And some of their momenta is the momentum of the operator. And then there are some Mandelstam variables that correspond to the sums of the squares of the momenta pairwise. And the sum of all 3 of them together is also the momentum squared of the operator. But because this threefold sum square is actually the sum of the twofold ones, there's a relation. We can first form some dimensionless quantities by dividing through by the overall momentum squared. And then U and V and W are defined in this way, but this relation tells you that they all add up to 1. So there's really only 2 independent variables, but there's a threefold symmetry, which makes it useful to keep W around sometimes. In fact, we found that it was simpler to change variables in the symbol alphabet, and the symbol alphabet can be written in terms of these letters here, which are rational combinations of U, V, and W, and also 1 minus U, 1 minus V, and 1 minus W. And when you do that, the symbols of this form factor at 1 and 2 loops turn out to be very simple. They're basically given by 1 term plus its images under a dihedral symmetry from permuting the 3 gluon momenta around. And the 2 loop one has 2 terms in it plus the dihedral symmetry. And by using a kind of bootstrap, we were able to get 8 loops worth of data for that process. And then the other character that's related to it by this weird symmetry is the 6 gluon MHV amplitude. And this one, in the normal theory, might have 8 or 9 different kinematic variables. But in this theory, because of all the symmetries, there's a dual conformal symmetry, and the answer has to be written in terms of just 3 dual conformal cross ratios. So these are like the cross ratios of the 4-point function that we wrote down before, but they're kind of more directly in momentum space. So this x13 is equivalent to squared is equivalent to s12, and so on. Anyway, it's a function of three variables. But on the other side of the duality, we had a function of only two variables because W was not independent of U and V. And so the way it works is that this process, to get the duality to work, it should be, for a special case, a lower dimensional kinematics. And the lower dimensional kinematics in terms of these variables, it turns out to be imposing a cubic constraint on them. When you impose that constraint, it also puts you onto a surface that is even under parity. And there are 9 letters for this hexagon problem, but 3 of them go away when you go onto this surface. So the symbol alphabet on this surface also has 6 letters, and I've written them as A to F, but now I put hats on them. But otherwise, these formulas happen to be exactly the same as the formulas for the form factor. And when you write the answer in terms of for the symbol on this surface, in terms of these letters, it looks remarkably similar. You get some different factors here. But again, you have 1 term plus dihedral, 2 terms plus dihedral images. And that one, we knew to 7 loops.
So,
Yep.
but because there are different problems except on the surface, why would you even think to look for the duality in the first
Well,
place?
it was all an accident. We actually looked, I was preparing a talk and I had 2 topics and I pulled up the wrong slide. And then I noticed that it looked like the other slide. You know how this stuff happens. It's
Yeah.
pretty random. Or at least it was in the past. So furthermore, I wouldn't have probably even seen it if it had been in the full space. So we were just looking on a one-dimensional line. And I happened to look at 2 lines that were the images of each other inside this 2-dimensional space. And on those lines, the answers are HPLs and the indices are all 0s and 1s. But I noticed that all the coefficients were the same. And then I asked, what do I need to bring these 2 into each other? And you had to reverse these 0s and 1s and turns 1s into 0s. And then you can make it line up. But, you know, once you see the coefficients are the same, you might ask, what do you need to do to bring it in? But for a while, we didn't know whether it existed off of that line. And then we realized that we could make that work if we did this map. We only sort of had the map on the line, and then we got the map in 2D, in 2 dimensions. So the map is actually not too complicated in terms of the cross ratios. It's simpler in terms of the letters. I think I have, yeah, the letter one in a second. But in terms of the cross ratios, you can check that if you have 3 variables, U, V, and W, that add up to 1, and you apply this map to them, then the surface where the sum is 1 maps into this dihedral surface. So that's the symmetry. You map U's to U hats according to this, and this S means write the symbol backwards. There's some -1 to the M in the general definition of the antipode, but for us, we're always comparing things that have even M, so it doesn't really matter. And if you want to implement it on the symbol letters, it's even simpler. There's some square roots going one direction, and otherwise it's a very simple relation. But it exchanges A-type letters with D-hat type letters and vice versa. Under the dihedral symmetry, A goes to B, goes to C, goes to A, and D goes to E, goes to F, goes to D, in both hatted and unhatted. So as I was saying, we could check it right away or pretty quickly through 7 loops, but we didn't have the 8-loop answer. So instead we used the symmetry to develop a much smaller ansatz for the 8-loop answer, which was much easier to then verify that it worked. But we still don't have any good reason why. We did find a reason why by going up to this higher process, but we don't understand that reason. But we had computed this quantity to 2 loops. This is much harder to compute because we now think this alphabet has 88 letters. And so when you try to build up the higher weight function space, the number of possibilities explodes pretty quickly on you compared to only having 6 or 9 letters. But still, we could get to 2 loops and then look for this symmetry. And we managed to find the kinematic map that implements the symmetry. The kinematic map is pretty ugly in terms of the cross ratios that you can define here. There turns out there's 8 cross ratios, but there's a lot of relations between them because there's really only 5 kinematic variables. And then we need to reduce to a lower dimensional kinematic. So there's 4 kinematic variables here, but there's nonlinear constraints on the cross ratios. There's a set of variables that are used to parameterize the system in an approach based on integrability called the form factor operator product expansion. And in that parameterization, this kinematic map is quite simple, which suggests that integrability and some of this framework has something to do with this. Anyway, in that set of variables, there are 4 variables, T, S, T2, and S2. And the kinematic map has this kind of pretty simple behavior. There's a 5th variable, but you have to set it to 1 to get onto the space where this symmetry works. So in searching for other places where the symmetry might appear, we use a counting argument. We take a function, say a 3-loop function, and we take its coproduct, and we find that of all the possible functions that could be here, only 8 are independent. And then we take its derivatives or its coproducts and we count again. And when we get the palindromic sequence, we get excited because it's necessary if this is going to have an antipodal self-duality. So we've actually now, in this paper, we got through 3 loops and established that this self-duality works to 3 loops. And in the paper to appear with Zhenji Li, we also have the 4-loop answer. And it is palindromic, and we verified that it obeys this symmetry. But it's hard to get to 8 loops when you have 88 letters. Now, this palindromic behavior is necessary but not sufficient. It turns out in this case, this 4-point form factor, everything is obeys the antipodal self-duality, at least at the symbol level through 4 loops. But sometimes it can be a little bit deceiving. So another case would be to go to higher point form factors. And that would seem to be the next obvious place to look for this symmetry. And Zhenji Li computed at 2 loops these form factors. And from the 4-point case, we expect that the thing we're supposed to look at is the 2-loop remainder function, which at symbol level is just the 2-loop answer minus 1/2 the 1-loop answer squared, because it's sort of a logarithm. And when we do this for n equals 5 and 6 with Zhenji's symbols, and we go on to a similar lower dimensional parity preserving surface, we find these palindromic sequences. However, beyond n equals 4, we can't get it to work. We can't find a good kinematic map. So it's enticing, but frustrating.
So is this true for so you always have to do this BDS normalization, even if you futz around with the normalization?
Actually, it turns out that in the case of the 4-point form factor, the BDS-like normalization does not work. We have to be in the remainder function or BDS normalization. You can't use BDS-like. In BDS-like, there's a one-loop finite function, and it behaves badly, which is also why it was good that Genji could get to 2 loops, because we didn't really know how to look for this thing at 1 loop.
So there's not like some other space you could like divide out like additional stuff that will help you make this work.
So you're asking if we change a frame, could we get it to work? I mean, it's possible, but we haven't found out a way to do it. I mean, if you just look at I believe if you just look at it first of all, yeah. Anyway, we think that the one loop guy doesn't know. Well, we can talk about it later, but we don't know a better normalization that would make this work for these hard point guys.
I just wanted to know what this qualification is if it does not work.
Okay, it's tricky because there is a transformation on the symbol letters at the 5-point case that we have found, but it does not lift to a map on the underlying kinematic variables. So the symbol letters, there's a set of them, and you might find some map that takes them to each other and returns the symbol when you reverse it. But there's 2 problems. One is that the ones we found, they can't be identified as a transformation on the underlying variables. That's a stricter requirement. Secondly, that map doesn't really square to 1. It like squares to 2. And the symbol doesn't really come back to itself, it comes back to itself up to an overall normalization. So we're not too happy with that. And now my student Andy Liu, he had found a similar behavior for the 6, 7, and 8-point amplitudes, also at 2 loops, also on this parity violating surface. So there's some weirdness that happens there, but we don't know what to make of it. But we tried many times. We basically try all possible maps using machine learning to try to look for a solution. And it always winds up in these kind of bogus solutions. So then you put in a repulsive term, so it won't go there, and you find other ones. It's like killing ants, you know, you kill in one place, they pop up in another place. Anyway, so we don't know what's going on there. Now, I should say that this antipodal self-duality, or duality at least, there's some kind of version of it that's been seen in integrals. You can have a one-loop n-gon integral in higher dimensions. D is equal to n, I think. And there's a formula for it in terms of the Feynman parameters, and it's quadratic, and there's a quadratic matrix here. And Nima, Erkani Hamid, and Elvis Yuan, they noticed a while ago that the antipode of the symbol, which is a weight n, or n over 2 function, it takes the q to q inverse. So that's kind of an antipode for an integral, but I don't know, the weird thing about it is it changes the kinematics. If you take a sample Q for like the massless box with 4 external masses, then the Q inverse will have internal masses. So there may be something interesting to see there, but it definitely moves you from the massless phase to some Coulomb branch. So in the remainder of the talk, we'll talk about fishnets, and fishnets turn out to be built out of ladders. A ladder is a special case of a fishnet rectangle where one of the edges, one of the sides only has one guy. So you set m, say n equals 1, m, we just call it p here. The formula for this integral was written down in the 1990s, and it looks like this. And it has this same alphabet as for the p equals 1 case, which I showed you earlier. That was the one mass, the one loop box is the p equals 1 case. So again, that's in terms of these cross ratio variables. So you can construct the number of coproducts of these ladder integrals, and you might get excited if you see this pattern because it's palindromic. But if you look a little closer and you inspect these spaces and dimension 3, you find that they can't be mapped into each other. They have different properties. So there's no map that can work for p greater than 1 and make them invariant on their own. But then we started counting them for rectangular fishnets. And in the case that the rectangle was a square, we found it was palindromic. So these guys look the same forward and backwards. The 2-3 case, though, is different. It has a different property. And this was helped by the fact that we had earlier with Benjamin Basso found a formula for these fishnets where it's a determinant of the ladder integrals. So every element of the matrix that you take the determinant of is a ladder integral, but it depends on where you are in the matrix, and it increases by 1 in each direction. So we covered this one before. This has this antipodal self-duality. So what we were able to show with Claude Dour was that the general square fishnet, where n is equal to m, has this invariance under the combined operation of the antipode and this C kinematic map I showed you, which is essentially a twisted version of complex conjugation. And the first thing we showed, which I'll skip the details, but there's a very simple transformation of the ladder integrals under this map. And since everything's determinants of ladders, if we know how the ladders transform, we know how any determinant made out of them transforms. So the transformation is that if you have a ladder of loop order P, you get all the loop orders of lower P in the transformation, weighted by a binomial coefficient and a power of this logarithmic quantity L. You notice that this is a pretty bad quantity from the point of view of single valuedness, because if you wrap Z around the origin, this thing shifts by 2 pi I. So it behaves rather badly. So all the good things under this operation, this transform, ASD transform, you should eventually get rid of all of the L's. And these are not invariant by themselves, except for P equals 1. Anyway, there's a way to derive this from that polylog representation, and there's some other tricks you can use to find it. Then when we had the transformation of the ladders, we plugged it in to the square fishnet formula, and well, we could find that it was always invariant, and we could even prove it for arbitrary m by using some properties of this transformed FP, that it's proportional to the same thing with P minus 1, and then you differentiate by rows and expand on columns, and eventually you show that this thing has no dependence on L. And that proves that it's invariant, because the L to the 0 terms are always the original function, and the goal is always just to show that there's no L dependence left. So in the last part of the talk, I will mention that we've been trying to study generalizations of this. And we haven't actually asked ourselves, where do these functions come from? But we've just asked the question, suppose I have a polynomial in the ladder integrals that obey this antipodal self-duality. And there's also another condition, the Steinman relations, which is obeyed by all these rectangular fishnet integrals. So we just thought we would throw in that condition too. So this is a well-posed problem because we know exactly how the FPs transform, and we can just write down generic polynomials and look for ones that are invariant. So we found infinite families of solutions to these constraints. And now we kind of understand where they come from in particular sense. And they all are linear combinations of determinants of the type that have appeared in some other n=4 correlators, often ones that show up when you have large R charge. But we don't have a one-to-one correspondence between what we find and what the what particular correlator you would have. They're not necessarily correspondent. So these determinants that were defined by Frank Coronado, by manipulating rows and columns, you can, in the math literature, they're sometimes referred to as templates minors. So there's a type of matrix which in which everything's the same on different diagonals, and that's called a templates matrix. Some people like Hankel matrices. If you swap some rows from front to back, you can move diagonals to anti-diagonals, and Hankel matrices are the same on anti-diagonals. So they're sort of the same thing, at least when they're finite. So these templates minors, one class of them, you modify the constancy on I minus j equal to a constant. You change it by putting in a partition. And what this does is it just wipes out some rows of a basic matrix. And so this partition is labeled by non-increasing positive integers. And that's the same way you label Young tableaus. And so it turns out we're going to find a bunch of invariants and transformation formulas that use a lot of quantities that show up naturally in things related to Young tableaus. By the way, this restriction so that you have a lambda I, but you have no separate partition depending on j, that's to keep these f's so that they are kind of all proportional in the sense that as you go from one I to the other, they all increase by 1 in one direction. And that turns out to allow them to obey these Steinman relations. So we just plug in and check. We transform the first example, n tilde of 1. So the square fishnet is n of 0. It has sort of none of these partitions. But the first sort of excitation you can do is just have the partition 1, which has a Young tableau of 1 box. And it transforms by something proportional to L and the size of the system M. And then you do the same thing for 1, 1, which is a Young tableau of 2 vertical boxes and 2 horizontal boxes. And you find these transformations. And if you look at the M dependence, you'll see that because this has a common M minus 1 and a common M plus 1, and otherwise things are pretty similar, this quantity will knock out both the L and the L squared. And so you find an invariance here. And this is the tip of the iceberg. This is the first partition that has no 1s in it, only a 2. And for every partition that has no 1s in it, we can find an invariant sequence of this type. Here's a little more elaborate example, which shows more polynomials in these M's and also some extra green coefficients here, as well as a characteristic L to the k over k factorial. So, and by studying this one and a number of other ones of similar complexity, you can find other invariants. So after a while, we decided that this was the general transformation formula. You need a few more examples before you conclude this. But it's you transform lambda, and the things that appear on the right-hand side are mu's. And remember, lambda is labeled by a Young tableau. For example, the 3, 2, 1 would have this tableau here. And the things that appear over here, they are always daughters under reducing or throwing away boxes. So here I've thrown away, I've got a 3, 1 tableau, and I've thrown away the guy sitting here. And so on down the line. This is the complete chain of things that sits underneath it. And I've written in green the number of paths from here to a given road. And that number always matches the number we found here. For example, n of 1, there's a 5 in front of it. And there's a 5 paths from here to here. The number of paths can always be gotten by adding up the numbers that appeared above. But in addition to having this number here, the number of paths, and this kind of trivial formula, where lambda here is just this absolute value means the sum of the entries. This is a kind of simple formula. The most complicated thing is this polynomial in m's. And this j minus I is read off of the Young tableau, where j increases this way and I increases this way. So every time you go to the right, you add 1, and every time you go down, you subtract 1. So you do that for the parent guy, lambda, sitting up here, and then you divide out the 1 for the lower tableau. And so here I've written in blue the surviving boxes and also recorded them here. And then you construct this function where you take m plus these numbers, and if you check it out, that gives you all of the blue letters here. So this matches the formula, and we also have a similar formula for the invariant. It's a little more complicated because you have to look for particular subpartitions, a smaller set, but you have to add back on boxes in some way. But we can now understand all of these things by a particular representation of these integrals. And the sort of key point is that there is an integral representation of the latter integrals where all of the p dependence is carried in a simple fashion in a numerator factor that is something raised to the p minus 1. And what that means is that if you shift this argument in the numerator, this quantity in the numerator, by a constant L, then the binomial theorem will tell you that you will induce L dependence, which looks exactly like the formula for the FP transformation. So essentially, you can call this, maybe it's better to call it a shift of sigma, but anyway, shift of this thing by some constant, that implements this transformation. And then we can apply that shift to integral representations of the fishnets. If we go back to the rectangular fishnet and we apply this, it's a determinant of these integrals, but it can be rewritten as an integral of a determinant. And that's called the Cauchy-Binet-Andreev formula. And when you do that, if n equals m, this numerator factor becomes a van der Waals determinant. And that van der Waals determinant has like a total anti-symmetry, and it doesn't really depend on sigma squared. So if we do a shift of this quantity, it's completely left invariant. So this is another way of seeing the invariance of the square fishnet, and it also lets us work out these transformations for the more complicated quantities we introduced. So the details are to appear soon. So I will just conclude by saying, once again, we have this very strange symmetry that we have found in precisely one object in the planar n equals 4 theory at the self-dual level, which explains an earlier duality. So like Robbie said about the muon, who ordered that? And did they stop ordering at that point? Or are they still ordering anything? And at least we can now sort of find something similar happening in a simpler context of individual fishnet integrals. But we still don't really know what the meaning of it is, but maybe we have some more clues to look at. There's also some clues that come from the fact that the only time it ever works is when you're in these lower dimensional kinematics. And that may help us to find other examples where this holds. So thanks a lot for your attention.
So thanks a lot, Lance. Are there any questions?
Maybe I missed it, but is there something physical behind the swapping of branch cuts and derivatives?
It's very weird. So that's one of the things that has us puzzled about it. It's yeah, no, it's a very strange operation. So the answer is no, we don't know what it means physically.
Anything else? So Lance is speaking again tomorrow at IPAM. I forgot what time.
I forget too, but
It's on the schedule.
I think it's late morning.
Yeah. Anyway, it's a small auditorium. If you don't have a ticket, then you should. You probably got an email and Zoom, with a Zoom link. And if you do have a ticket, then of course you should go. Okay, well, let's.
So that will be the AI branch.
That's the
In
AI.
this work, I used Claude, but
Right.
not Claude from Anthropic, but Claude from University of Bonn.
Okay, let's meet Lance again. I think the one in Bonn is better.